Hi everyone, how are you guys doing? I apologize that there is no camera today. I'm having an issue with my camera, but next week or the next lecture it should be working. This week is really just a review of physical geography. There's some new things that are going to be thrown in there, but if you've already taken a physical geography class, then this is going to be really easy. But before we get to a lot of the issues that happen and a lot of the environmental issues, you kind of have to have a refresher of how our atmosphere and insulation and energy from the sun, all these things, how they work, right? Just kind of like a refresher. So I will go through this pretty quickly. So let's just get started. It's just a review of physical geography, not the entire course, but some of the most important things from that course. First one is the relationship between the earth and the sun. This is the most important relationship, right? How our earth revolves around the sun, how it rotates on its axis, how much sun comes in and goes through the atmosphere and heats the surface of the earth. Okay, so remember, when we talk about this, it's the relationship between the earth and the sun. It does not stay the same throughout the year. This is one of the most important relationships when we talk about relationships between systems, right? So you have two basic movements, rotation and revolution. The earth rotates on its axis, right? And one full rotation takes 24 hours. The earth revolves around the sun. One full revolution takes 365 days, right? So you have the earth rotating on its axis and revolving around the sun at the same time. So I'll have a really cool video in your module for you to watch this, an animation, really, a better animation. And so the poles are going to rotate at 0 miles per hour or 0 kilometers per hour. And the closer you get to the equator, the faster that it rotates. Okay, so when we start thinking about the Coriolis effect, that's really important, right? So Coriolis effect is like that conservation of momentum. So if you have a hurricane starting at the equator, which is here, right? It's the equator, and it's traveling towards the North Pole, but the Earth is rotating this way. Do you follow that? It's not going to go straight towards the North Pole, right? It's going to kind of do this and travel this way. So that's why a lot of our hurricanes that are born, in a sense, or develop here in the northern part of the equator in the equatorial Atlantic, they all end up hitting this here, this area here, right? Our East Atlantic area is the place where all the hurricanes hit. Not all of them, but this is a huge hurricane area. Okay, so that's the Coriolis effect. Rotation has several important effects on the physical characteristics of Earth. Obviously, I just explained the Coriolis effect, your gravitational pull, and your daylight and darkness. So that is our 24-hour rotation, right? It looks like the sun is rising and setting. It's really not rising and setting, right? Now, Earth's revolution, it takes about 365.25 days. It revolves around the sun in an elliptical fashion. So it's not really like a circle around the sun. Here's the sun. It's more like this. And that path will change. And so we'll talk about that when we look at climate change. There are these natural forces that make our climate change, but there's also these anthropogenic or human forces that make our climate change, right? And one of those natural ways is our trip around the sun. It will change. And so that will change entirely our relationship with the sun. So the fashion or the trip that it takes is an ellipse, okay? And two important dates are perihelion and aphelion. The day that we're closest to the sun in our revolution, around the sun. In those 365.25 days, we're closest to the sun on January 3rd. And we're furthest away on July 4th. That's weird, right? Right? So what I want you to take from this is that our proximity to the sun has nothing to do with what we're experiencing with our seasons, okay? So our seasons don't have anything to do with how close we are to the sun or where we are in that trip. What matters is how the Earth is tilted. So our Earth is tilted, right, at 23.5 degrees. And the North Pole is either facing away or towards the sun. And it rotates around the sun like that, right? What a great picture I drew there. But when our North Pole, or the northern hemisphere, is tilted towards the sun, the northern hemisphere is in summer and the southern hemisphere is in winter. Okay, so that's how we get our march of our seasons. Not how close we are to the sun doesn't mean we're in summer. It's where the tilt of the Earth is in relation to the sun. So if the North Pole is tilted towards the sun, we're in summer in the northern hemisphere. If the South Pole is tilted away from the sun, they're in summer in the southern hemisphere. Okay, so our Earth is tilted at 23.5 degrees. We're tilted towards the North Star always. Say this is the North Star. We are always tilted towards the North Star. And here's the sun, and we're revolving around the sun, but we stay tilted towards the North Star. Okay, so the most fundamental feature of the annual march of the seasons is the orientation of the North Pole from the sun. Okay, here's just another picture. I might have been drawing it backwards. It's just kind of confusing when it's on my screen versus your screen. Okay, but I'm going to have a really cool animation that's going to explain it better. This is hard to explain when we're not in person, but yeah, you'll have an activity on the module. So what causes the seasons? Couple things. The reason for the seasons. Earth's shape. Earth is not a perfect sphere. It is fatter at the equator. So we call it an oblate spheroid right here. Okay. And so when you intercept the sun, that has a lot to do with the way the sun hits the Earth. So it's not a perfect sphere. It is an oblate spheroid. Earth's rotation, it rotates on its axis. Inclination of axis, it is tilted at 23.5 degrees, and that changes. So in like 40,000 years, it'll be 22.5 or less or more. So again, that will change the climate. Okay, so those are natural phenomenon that changes our climate. So our climate's always changing. And climate change deniers will say, you know, they'll use that. And it's not a wrong, it's not like they're wrong. It's true, our climate is always changing, but you cannot deny the fact that our overuse of fossil fuels in carbon dioxide and what we're doing, how we're using our resources and exhausting these natural resources, you cannot say that that has nothing to do with our climate change. Okay, so your inclination of axis, Earth's revolution, it revolves around the sun, and Earth's tilt, the North Pole is always tilted towards the North Star. And again, like in 100,000 years, I might be off, maybe at 80,000 years, this will tilt towards the South Star. But right now it's tilted towards the North Star, so that has a lot to do with how we experience our seasons. Okay, so again, distance from the sun does not play a role in the seasons at all. Okay, I've said that like 5 times, so maybe that's like really important to write down in your notes, right guys? Temperature changes with latitude, right? The sun's energy does not reach all places uniformly. The combination of Earth's shape and the tilt produces a variation of exposure. So here's the sun. And here's the Earth tilted. Northern hemisphere is in probably summer, right? In all these different latitudes. the sun's rays are not going to hit it the same all over. Does that make sense? So on average, the equator gets more sunlight all year long. On average, okay? So you have higher temperatures all year long at the equator, and this is really where you have your true seasonless climates of the world. They don't really see much change, these places, like from winter to spring to summer to the leaves falling in the fall. So when's the last time, have you ever seen the rainforest lose its leaves during the fall? No, because they are not experiencing those defined seasons. As you move further away from the equator up here in these latitudes, you start to see those seasons, like really you see the dramatic changes, okay? The atmosphere. So now that was that. And again, that would probably be a whole chapter in physical geography, a whole week. Now let's move on to the atmosphere, which is really important when we start to talk about climate change and really get into climate change. It's important to understand what the atmosphere is made up out of, right? We know the atmosphere is made up out of air, obviously, duh. But what is that air and what does it contain and what are those different layers within the atmosphere? Our atmosphere is surrounded by a bunch of invisible gases, right? So you have two types. You have permanent gases, and then you have variable gases. Wow, this is like really difficult. It's like graffiti. Your permanent gases are not going to have much influence on weather and climate. Why? Because no matter where you go, what year, what day of the year, what season, what latitude, doesn't matter what or where you're at, okay? You're always going to have these gases and this percentage. Always. That's why they are permanent gases, okay? Permanent gases. Always 21% oxygen, always 78% nitrogen, and 1% is argon. So, I mean, you can go to the most humid place on Earth or the driest place on Earth. Your makeup of this in the atmosphere is always the same. So it's not going to affect climate. On the other hand, you have these variable gases. Now, these will change over time, okay? They're changing and they do affect weather and climate. I didn't have a slide for it. I thought I did. It might be next, but I do want you guys to know that variable gases will vary. So they're water vapor, methane, CO2, hope you're writing this down, or carbon dioxide, nitrous oxide. So these do affect weather and climate because they appear in different amounts in different places. Like if you go to Florida, you know that there's more water vapor in the atmosphere, right? You can feel it. It's more humid. So that's an example. And you can't see these little gases, but they're up there. These are all variable gases, right? Then you have the sun. And so you have like CO2, methane. Some of these are produced naturally. Some of them are produced by the burning of fossil fuels, okay? Here you have the earth. Then you have energy from the sun comes in, warms the grass, the sand, the water, and then that energy is re-radiated back out. But guess what? It can't, all of it can't go out. A lot of it is trapped. And so what do we call that? That is the greenhouse effect, obviously, but then in the lower portion of the atmosphere, we call that warming. So these variable gases do affect weather and climate. The structure of the atmosphere, here are the different layers. It goes from troposphere, here's the earth, the surface. Then you have the troposphere, stratosphere, mesosphere, thermosphere, exosphere. This is what it looks like, right? Troposphere, stratosphere, and then it goes all the way up. And then the place where you have the concentration of ozone is within the ozone layer, obviously. Now, ozone is a variable gas as well. Okay, so in your notes, when you wrote down variable gases, ozone does occur all over the atmosphere, but it's concentrated in the ozone layer. Okay, and the ozone layer is really important because it protects us from harmful UV radiation. So if it weren't for the ozone layer, we would all burn up and die. I mean, we probably wouldn't be existing because that UV radiation from the sun is super harmful. So that's why the ozone is so important. So let's move on to solar radiation. This is what makes life here possible, right? We are in this perfect proximity from the sun to the sun, and it obviously we need the sun, right? But it's what makes life on here possible and gives energy to the atmosphere, not only the atmosphere, but powers almost all biogeochemical cycles, which is what we're going to get into at the end of today's chapter. So when we talk about energy from the sun, radiation coming in from the sun, we can call it Earth's energy budget, right? Here is the surface of the Earth. Some of it doesn't even make its way from the top of the atmosphere to Earth. And then a lot of it comes in and warms the surface of the Earth, and then the atmosphere above it is heated through conduction. So first the Earth is warmed, but then the atmosphere or the air around us is warmed because the atmosphere is not the best conductor of heat. So first it comes in, warms the dirt, asphalt, grass, sand, all those things, and then it's re-radiated back out into space in a lesser form of heat or more degraded form. Okay, so over time, this is balanced. All the energy that comes in from the sun, the same amount is re-radiated out into space. Nothing is lost because energy cannot be created nor destroyed, right? So you have this annual balance between incoming and outgoing radiation. That's the global energy budget. You have some loss from a reflection at the top of the atmosphere. Then you have that direct absorption of solar radiation on the surface of Earth, and then surface to atmosphere energy transfer. Here is a picture of the energy budget. Incoming solar radiation. You have just a little bit of the energy from the sun is absorbed by the atmosphere, like very tiny. So most of it is absorbed by the surface of Earth and then re-radiated out back to space. All I really want you to notice in this picture is whatever comes in is exactly what comes out. Nothing is lost or nothing more is let go. And over a period of time, this is balanced, okay? So it is a system in equilibrium, okay? One term that's important is reflection. And when we look at our surface of Earth, what type of surfaces are there, right? We have white at the top. Does this white work? Nope. We have light, we have green, we have dark blues, right? Browns, greens, white, snow, darker color. So what I'm getting to is that different surfaces have different reflective capabilities, right? You know, on a hot day, what color are you not supposed to wear? Black, right? Why? Because it absorbs heat. And with that same thinking, that same knowledge, when we look at the surface of Earth, different surfaces will have different reflective capabilities and absorption capabilities. So when energy from the sun comes in, passes through the atmosphere, that white snow at our poles, that is also going to help and immediately reflect that energy from the sun. Our dark oceans, I know they're blue, but mostly they're dark, right? They absorb heat. So if we were to lose all our ice on the planet, we already are going to increase warming because there's not any white snow to reflect sunlight. So we call this the albedo, overall reflectivity of an object or surface. So white snow is going to have the highest albedo. It's going to be like 95%. It could be up to 95%, 70 to 95%. And darker surfaces are going to have the least percent or the smallest albedo. Okay, that's really important to remember. And we'll talk about this a lot, and keep this in the back of your mind, albedo, and how it relates to our global temperatures. The more ice that we have on the planet, the more sunlight is reflected back out into space. The less ice, the more is absorbed. So that means it's going to just keep getting warmer. We have not even really reached the tipping point when it comes to global temperatures or when it comes to warming of the planet. And it's actually really scary. Here is this really awesome picture that explains the albedo effect. It's from my physical geography book. I really just put it up here for comedic relief because I think I did a better job at explaining albedo than this picture, right? It's kind of like, okay. Here are some reflective values of albedo, different surfaces. All right, so last portion of the chapter today, really quickly, I think I flew by it too much, but you're going to have a lot of links and activities to look at in your module that's going to help explain really just the basics of physical geography. But the last portion of today, we're going to be looking at these biogeochemical cycles. So for the biosphere to work correctly, its chemical substances must be continually recycled through the following cycles. And one that's really easy for you guys to understand is the water cycle, right? We know that it evaporates from the ocean, condenses, moves over land, falls, then there's runoff, it's sucked up by plants, and then it's evaporated back into the air. So that's a cycle. Now, just a fancy way of explaining this cycle is a biogeochemical cycle. Here comes the mailman, and you're going to hear my dog go crazy right now because this is all he looks forward to all day. It's so funny how animals, like cartoons, they show dogs and they hate the mailman. That's my dog. I'm going to pause this really quickly. Okay, I'm back. Get him, boy. He's so funny. So for the biosphere to work, right, its chemical substances must be continually recycled, right? Water cycle, carbon cycle, nitrogen cycle, phosphorus cycle. There's a lot of cycles. We're not going to cover all of them. We're going to cover really important ones, okay? So it's really how, I mean, you can think of it how energy flows through the ecosystem, right? From the sun to the plant to the next organism. Right? It's kind of like that. It's the same thing. After one organism uses a substance, that substance needs to be converted to a reusable form. And it's all using energy, right? For every cycle to work, we need energy from the sun. Okay? First cycle, oh, here's just some examples. Energy cycle, hydrologic cycle, water cycle, carbon cycle, nitrogen, oxygen, mineral. Many of these cycles are closely interrelated, even if we will talk about them separately. The carbon cycle or the water cycle cannot work with the energy cycle, right? Energy from the sun. So all these are interrelated. Everything really is interrelated. That's a huge overlying concept of geography, these interrelationships and interconnectedness. First cycle is the carbon cycle. Carbon is the basic element of life and part of all living things. I mean, you can break it down very simply to the Lion King, right? And his dad, I haven't seen this in a long time, but he's like, and we return to the earth. And it is now the circle of life, right? And then you can hear the song playing. You guys know what I'm talking about? Yes, that's the carbon cycle, very simply put. Okay, carbon is the basic element of life, and we help in the carbon cycle. Okay, we're just returning carbon back into the atmosphere. Most carbon is stored in the atmosphere, okay? And then you have plants that take carbon from the atmosphere and convert it into food. And then we eat some plant or we eat an animal that has eaten that plant. And then we return it back into the soil. there are also things happening that are adding more in carbon into this carbon cycle. Not naturally, but anthropogenic causes. So we are altering the carbon cycle. We as man, we are altering, or humans, the carbon cycle. Okay, the carbon cycle is a transfer of carbon from carbon dioxide, I forgot to mention that, carbon is stored in the atmosphere as CO2, to living matter and back to carbon dioxide again. And then how do we return back to carbon dioxide back into the atmosphere? Well, when we eat that carbon, we respirate or respire, right? Through cellular respiration, we return CO2 into the atmosphere. Here's a picture of the carbon cycle. You have CO2 in the atmosphere, then plants, it turns it into food, then animals will eat that plant, and then we eat that animal, then we breathe it out. And then you also have plants that breathe out CO2. No, sorry, humans breathe out CO2. Then you also have like volcanoes that add CO2 in the atmosphere. Then you have the ocean that filters out CO2. So now we are seeing that our increase of CO2 in the atmosphere is changing the carbon cycle, right? These are human-caused changes to the carbon cycle. Greenhouse gases like carbon dioxide play an important role in the regulation of temperature. CO2 is a greenhouse gas. It is a variable gas. It has a huge impact, a huge influence on our climate. Okay, too much CO2 is going to cause warming in the lower portion of the atmosphere. So it's also going to have effects on the ocean. Our oceans are becoming highly acidic. They take CO2 from the atmosphere, and it's almost like they filter out CO2 from the atmosphere. But now there is too much CO2, right? Because over the last century and a half, we have added a considerable amount of carbon dioxide to the atmosphere by extracting and burning fossil fuels. So because there's so much CO2 in the atmosphere, it's gone as far as reaching the effect on our oceans. So oceans absorb a great deal of CO2 from the atmosphere. They absorb up to 1/3 to 1/2 of all the carbon that human activities release. Once they're in the ocean, marine plants and animals remove carbon from the ocean water through photosynthesis. So these large amounts of CO2, they are found in oceanic sediments. So now our ocean waters are changing. The chemistry of our ocean is changing. They are becoming highly acidic. So this is ocean acidification. Over the last 30 years, we've lost 50% of all our coral reefs. 50%, guys. Why? Because the oceans are warm, that's one reason, but also because oceans are so acidic. So it is possible in our future we are going to see fishless oceans, or a huge loss of biodiversity in our oceans because of the amount of CO2, because they're so acidic. Plants and animals in the ocean cannot acclimate to the amount of acidity. So different causes of our increase in CO2 in the atmosphere. I'm trying to figure out how this slide goes. Global changes in our temperature, increased temperatures, rising sea levels, altered precipitation patterns, increased wildfires, flooding, droughts, heat waves, extinction of organisms, loss of plankton. All these are effects of our changes in the carbon cycle, okay? Oceans absorb a great deal of CO2. They have absorbed 1/3 to 1/2 of all carbon that human activities have released. The nitrogen cycle, this is the same kind of concept. It's just the movement of nitrogen in and out of the biosphere. So nitrogen is an inexhaustible component of the atmosphere. Only a few number of organisms can use it as nutrient in gaseous form. The movement of nitrogen in and out of that biosphere is called the nitrogen cycle. So we have nitrogen gas surrounding us. 78% of the atmosphere is made up of nitrogen. However, that that can't be used because of 3 covalent bonds. So in order for it to break down, there's like these 5 steps that plants and animals help between the living and non-living portion of the environment. They help break down this nitrogen. First, you have nitrogen fixation. You convert gas into ammonia. Nitrogen fixing bacteria carry out biological nitrogen fixation in soil. Then you have soil bacteria convert the ammonia into nitrate. Then you have assimilation. Plant roots absorb that nitrate. So we're just taking nitrogen gas and turning it into a form that can be cycled, right? And then organisms pee, die, or just return ammonia back into the soil. So these are just steps for the nitrogen cycle. You guys can take some time, write this down. Don't worry about remembering every single step. It's just really taking nitrogen as a gas and recycling it through the living portion of the environment, through the biosphere, lithosphere, back into the atmosphere again, right? Does that make sense? It's just like a cycle, like the carbon cycle, but there's more steps to it. And it might not be a known cycle. Like I'm sure you guys learned the carbon and water cycle when you were kids, right? Human-induced, you don't have to worry about this. Okay, the water cycle. The water cycle is water in the atmosphere moving through the biosphere, right? And we are also part of the water cycle. Most of our water is stored in the ocean. This is the great, obviously almost all of our water is in the ocean, right? This is the great reservoir here for the water cycle. Then you have evaporation, which cannot happen without the sun, right? Then you have condensation, precipitation, air moves the clouds over land. Then you have plants that suck up water through their roots. Then through evapotranspiration and their little leaves, that comes back out into the atmosphere, and then some of it runs off back into the ocean. Then you have subsurface flow. So this is the water cycle. We have also had changes to the water cycle. Too many pollutants in the atmosphere has caused acid rain. Our water is acidic. It is damaging forests, riparian river, lake ecosystems, polluted water sources. We are polluting our groundwater, and we're changing our oceans, right? The chemistry of our ocean, which is through too much carbon. So you see how every single cycle is interrelated. And that's it, guys. That is the end of chapter 4. Wow, I did that really quickly, but that's okay. Sometimes it's better just to have a really easy breezy lecture. You will have a lot of links today on your module, or this week on your module. And yeah, so I think you're going to have a journal today, this week too. All right, you guys, thank you for being patient. I apologize about the camera, but just that's the way it works sometimes. All right, you guys, have a great day. Thank you.